Hello there, Mr. Wilson here again for another part of the Binomial Theorem series targeted for GCSE further maths students. And in this part, we're going to look at Pascal's triangle, probably my favourite part of this topic, and how this links to the binomial theorem. So, first of all, we just need to remind ourselves about what we did in the last part, which was we had a look a bit at expanding. And I said that the binomial theorem can help expand brackets when it's the same bracket multiple times, but I didn't go on to then explain how it actually works. And this is going to be part of that. So, just as a reminder, if you were to calculate x plus 1 squared, which is the same as saying x plus 1, that would equal x squared plus 2x plus 1. And we showed that in the last part. And if you don't believe that, then you can work it out yourself and convince yourself that that is the correct expansion. And we also wrote down that x plus 1 to the power 3 was x cubed plus 3x squared plus 3x plus 1. And eventually we sort of discussed the idea how we could do x plus 1 to the power 4, x plus 1 to the power 5, and so on. And we basically said, wouldn't it be nice if there was an easier way of getting these expansions? Well, there is. But in order to see that, we need to have a look at Pascal's triangle. Now, Blaise Pascal was a French mathematician who was credited with many different things in mathematics, but possibly his greatest idea was Pascal's triangle. Now, the idea of Pascal's triangle could have been dated before Blaise Pascal, but it's named after him, so we always remember it because of his idea. So this is how Pascal's triangle works. Well, Pascal's triangle is a triangle which starts 1, 1, 1 at the top like this in a triangle formation. Then going down the side, you always have these diagonal ones going down the outside. Now, in order to find the number that should go here below these two, you add the two numbers above it. So 1 plus 1 is 2. And then the next row will start 1, because this diagonal of 1 should always exist. 1 plus 2 is 3, 2 plus 1 is 3, and then a 1 on the end to carry on with the diagonal of 1s. Then 1 goes here, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then a 1 on the end. And then a 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is also 10, 4 plus 1 is 5, and then a 1 there. And then we'll do one more row. 1 starts off the row, and then 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is also 15, 5 plus 1 is 6, and we end with a 1. And this is Pascal's triangle. Now, there are lots of different patterns to Pascal's triangle, and you could have probably a whole lecture in and of itself about the wonderful properties of Pascal's triangle. I mean, just to name a few, for example, down this diagonal here, you've got all the counting numbers, 1, 2, 3, 4, 5, 6, 7, and that will continue on forever. Down this diagonal, 1, 3, 6, 10, 15, those are all the triangular numbers, and that will continue on forever. So there's some really, really interesting patterns. There's also one of my favourites about Pascal's triangle, one of my favourite facts, is known as the hockey stick idea. So if you start on one of these ones here, and you go down, and then you kick off it, so it looks like a hockey stick, then all the numbers on the stick, so 4, 3, 2, and 1, must add to the number in the end. And this will work for any hockey stick. So, for example, if I start here and I kicked out that way like that, then 1, 3, 6, 10 adds to make 20, which is just truly incredible. Very useless, although I can imagine there must be some use somewhere. But yeah, all really, really interesting. But that's not what we're here for. We're here for expanding brackets. So how does Pascal's triangle help us to expand brackets? Well, we refer to this row as the 0th row, and that explanation will become that'll be explained in a little bit. This is obviously then the first row, that must be the second row, that is the third row, that's the fourth row, and that is the fifth row, and that's the sixth row. Now it's quite easy to spot which is the right row because after the 1, the first number, oh, let me just go across a little bit so you can see. After the first 1, the first number is kind of the number in that row, so to speak. So the fourth row goes 1, 4, 6, 4, 1. So how does this help us expand brackets? Well, if we go back up to the top, you might see a little pattern here. X plus 1 squared is x squared plus 2x plus 1. In other words, it is 1x squared plus 2x plus 1. 1, 2, 1. So, and you might then notice that the second row in Pascal's triangle is 1, 2, 1. Well, maybe that's just a coincidence. Maybe that's just a one-off. Well, let's have a look at the next one. X plus 1 cubed is x cubed plus 3x squared plus 3x plus 1. Well, that's 1x cubed plus 3x squared plus 3x plus 1. 1, 3, 3, 1. So the coefficients, the numbers in front of the variables, are the numbers in Pascal's triangle, right? Because the third row is 1, 3, 3, 1. And you get these descending powers of x. Because remember, when you expand brackets, the first, if it's that way around, the first term is always the highest power of x. And then it goes down by 1 each time. So we get 1x cubed plus 3x squared plus 3x plus 1. So it's x cubed there, x squared, 1, x on its own, no x. So just by using Pascal's triangle, I know what the next expansion is, right? Because if it follows the coefficients of Pascal's triangle, well, the next row, the fourth row, is 1, 4, 6, 4, 1. Okay, so let me just write those down. 1, 4, 6, 4, 1. Well, that must mean that the expansion of this must be 1 x to the power 4, because when we expand 4 brackets, we're definitely going to get an x to the power 4 term, plus 4x to the power 3, because we're going down by 1 power, plus 6x squared, plus 4x, plus 1, no x. And that is the expansion, and you can, if you don't believe me, you can expand it yourself, you can expand all 4 brackets, but it definitely is 1x to the power 4, I mean, we don't necessarily write the 1 though, so we can just put x to the power 4 plus 4x cubed plus 6x squared plus 4x plus 1. And that is the expansion. And we can continue this pattern for the next one. So the next one will be x to the power 5, because it's 1x to the power 5, plus 5x to the power 4, plus 10x to the power 3, plus 10x squared, plus 5x plus 1. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Isn't that just absolutely incredible? That something that is to do with adding up numbers is linked to something that's to do with expanding brackets, which is a multiply. I just find that totally mind-blowing, and it's an absolutely fantastic way of showing the links between different fields of mathematics and how they all sort of pull together to help you spot patterns in other things. Now, I'm going to give you a minute. You can pause the video if you'd like to expand what would x plus 1 to the power of 6 be, using this idea that it must be the coefficients in Pascal's triangle. And once you realise the pattern, then it's quite quick. Now, if you're somebody who's looking at that and is still a bit unsure, then definitely just skip back in the video to double check my working out and what you should be doing. But I invite you now to pause the video and write down what you think x plus 1 to the power 6 is going to be. So hopefully you've given this one a good go. It's going to be x to the power of 6, 1x to the power of 6, plus 6x to the power of 5, plus 15x to the power of 4, plus 20x cubed plus 15x squared. I got a bit carried away then. Plus 6x plus 1. And you'll notice that Pascal's triangle is perfectly symmetrical. So the terms that are at the beginning and at the end have the same coefficients. because it's symmetrical about the midpoint of the middle of the triangle. And that is the expansion. If you don't believe me, you can expand those 6 brackets yourself, but that genuinely is the expansion of x plus 1 to the power 6. Now you might think, well, if this is going to tell you how to expand brackets when they're this, by the way, remember it only works when it's the same bracket each time. So x plus 1 to the power 6, for example. You couldn't use, obviously, the binomial theorem if it was x plus 4, x plus 6, because they're different brackets. You might say, well, if it's that easy, then surely it'll work for everything. Well, let's see. So if instead I wanted to expand x plus 2 squared, now you can expand it through whatever method you would like, but I'm going to tell you that it's x squared plus 4x plus 4, which it genuinely is, because you can expand the brackets and prove it to yourself. But at this moment you might think to yourself, well, hang on a second, that doesn't match the second row of Pascal's triangle, because if it's a power of 2, we know we're looking at the second row, that's 1, 2, 1, whereas this is 1, 4, 4, so it doesn't work anymore. So as soon as you change the number from a 1 to a 2, it now doesn't work. Well, in actual fact, it does work. Pascal's triangle still works. It works for any number and any term. Pascal's triangles still work. You just have to think about it in a different way. And this way is where we get onto the more advanced binomial theorem. And this is the sort of more advanced idea. So I'm going to leave it there for this video, because I just want to kind of introduce that idea that if you're expanding x plus 1, that is the same as the terms of the values in Pascal's triangle. Whereas something like x plus 2 can still be done through Pascal's triangle, but you have to think about it in a different way to what we were originally. It's not just going to be straight in front of your face like it is with x plus 1, but we're going to have to sort of look at it in a different viewpoint. But hopefully you'll still see it is still Pascal's triangle. It just takes a little bit of thinking about. So that's going to be the next video. We're going to look at things like x plus 2, x plus 3, x plus 4, and what you would get if you expanded those with powers of 3, 4, 5, and how we can use Pascal's triangle for it. So, if you've enjoyed this video, then definitely check out all the other videos on the channel. Subscribe if you haven't done so already. I absolutely love making these videos. I've really missed making these videos, actually, and I've absolutely loved coming back on and making these videos. So thank you for all the support. Thank you for still commenting even when I haven't uploaded for a month. It's just so fantastic to see. So all I want to say is thank you so much for watching, and I hope you have a fantastic day.